Okay. So welcome back. So we will quickly review something we did last time, and then we'll talk about the plan today is to talk about simplex method. Yeah. Okay. So last time we basically followed the book and showed that if you just want to solve LPs, that is find their optima or determine if they are feasible or they are unbounded, it is enough to consider LPs in equational form. So when you have LPs in equational form, it means the constraints are all equalities except for the non-negativity constraints. All variables have to be non-negative. Those constraints should be there. Other than those non-negativity constraints, the only constraints we allow are equality constraints. Okay. So we discussed how any LP in general form can be converted to an LP in equational form. That was the first thing. Then once you have LPs in equational form, you can talk about basic feasible solutions. So a solution was basic if you look at the support of the solution, meaning those coordinates where the solution has non-zero values. That vector, the solution vector has non-zero values, and you had this matrix which looked like AX equals B. So those columns of A, those columns of A, so A will be a matrix like this. The columns where X has non-zero values, those columns should be linearly independent. And then we say that the solution is a basic feasible solution. And last time we saw there was a connection between basic feasible solution and the geometric picture where basic feasible solutions corresponded to vertices. And this was for LPs, which were written in equational form. Okay. A similar theorem exists for general LPs, but we just briefly referred to it, but we did not discuss it in detail. Okay. But an important theorem was that it's enough to consider basic feasible solutions. That is, in principle, if you're given a matrix, we could look at all sets of independent vectors. So if the matrix is m times n, then look at all subsets of m linearly independent column vectors and solve that system of equations. And if that system results in a feasible solution, that is, it satisfies the non-negativity constraints, because you have solved the system, it automatically satisfies the equality constraints. But when after solving the equality constraints, you might be left with a solution and check whether it satisfies the non-negativity constraint. If it does, then it becomes a basic feasible solution. And compute the objective function for that basic feasible solution and run through all the basic feasible solutions, and among them find out the best. And if the LP is bounded, then this is a valid algorithm, okay, to find out the optimum. Now that argument went through this theorem, which says that if the objective function of an LP is bounded, so we are thinking about maximization LPs. So if it is bounded above, then for every feasible solution x0, there is a basic feasible solution x tilde, which does at least as well. Okay. So so if the LP is bounded, then for every feasible solution, I can also demonstrate a basic feasible solution, which will do as well. And I slightly fumbled while doing the proof. So let us just quickly review. We won't do it in great detail, but let me just tell you how this proof was done. So you start with, so somebody has given you a feasible solution, and you want to show to them that there is a basic feasible solution that does equally well. Okay. So you look at this basic feasible solution and find out which are the coordinates where that basic feasible solution, that feasible solution. Look at all those coordinates where the feasible solution has positive value. So now there are two cases, and the second case again splits into two cases, but that's it. Yeah. So the first case is, suppose it turns out that the columns where x0 has positive value, those columns of the matrix A are already linearly independent. Yeah. So I should just have said that AK, yeah, I shouldn't really say non-singular. The columns of AK are linearly independent. Okay. Then we just extend these columns with more linearly independent vectors if necessary. If this K doesn't have already size M. So A was an N cross M matrix. Yeah. Yeah. So no, M cross N. Yeah. So if already this K has M columns, then we are done. Otherwise, we'll extend it by adding more columns so that it becomes linearly independent. And then this particular solution will be supported on that basis. And it will be a basic feasible solution. So this is the easy case. Yeah. Now, suppose it turns out that this matrix is singular. That is, the columns corresponding to these positive values, they actually have a dependency. Okay. And let us call that dependency W. Okay. So W is a vector whose values are confined to the columns K and whose positive value, non-zero values. Yeah, non-zero values are only sitting on the columns corresponding to K. And we know that such a vector exists because AK is singular. That is, the columns are, I shouldn't be using the word singular. The columns are linearly dependent. Okay. Then there are two cases. Yeah. Now look at this vector W. Yeah, so this is what Shubhada pointed out last time. So look at this vector W. We need to understand what happens when we move in the direction of W. What happens to the objective function when we move in the direction W from this point x0? Okay. So suppose it is the case that moving in the direction W from this point doesn't change the value of the objective function. Whether you move in the positive direction or the negative direction, no matter which direction you move in, because this thing is orthogonal to the objective function vector C, objective function doesn't change if you perturb x0 by W in either direction. Okay. Then what we can do is, since this W is non-zero, we can assume either moving in this direction or this direction will reduce some variable. Yeah, because so if W, either we move in the direction W or we move in the direction minus W, and ensure that some variable's value reduces. Because W is non-zero, one of these two is going to cause some variable to reduce. And we move in that direction until some variable becomes zero. So as a result, now we have got another solution whose objective value is as good as the original one, but this solution has the property that it has one more coordinate, which is 0. So we can return to this step with this new value x1. This K would have shrunk because one more value has become 0. And we repeat. Okay. So eventually, you will come to a stage where you will be left with only linearly independent columns. And then you would have found you would have found the basic feasible solution. Okay, but it may be that this condition doesn't hold. That is, moving in some direction, moving in the direction W changes the objective. Okay, then we have to be slightly careful. Okay, so now we know that no matter which direction we move in, we cannot move. Sorry. So let us assume that the objective function value actually reduces in the direction W. That means if you move in the direction minus W, the objective function value increases. Okay. So if you move in this direction, the objective function value increases. If you move in this direction, the objective function value reduces. Okay. So otherwise we will just take W and use minus W. So, okay. Now, as we move in this direction, objective function value is increasing, but we know that our LP is bounded. Okay, so we need to use that assumption. Our LP is bounded. So it must be that when we move in this direction, in the direction minus W, we must reach a point at which the the point becomes infeasible. Just stop at that value. So what must have happened? Okay, the equations are always being satisfied. The equations are always satisfied on this line. Okay, the equation parts cannot go wrong. So it must be that some new variable has become 0, and the variable that has become 0 must be one of the variables which is contained in this set, because W is anyway 0 outside of this set. So if the movement in the direction W causes some variable to become 0, it must be one of these variables. And we are back to that case where we have got hold of another feasible solution with fewer non-zero coordinates. Okay, and we can repeat this. Okay, so this is an algorithmic way of thinking about it, and we will eventually come to some sort of a point where we have got a basic feasible solution. Okay, so this establishes this theorem. Okay. So you can say it is by induction. Induction, reverse induction on the number of non-zero coordinates. So we are reducing all the time. Okay. So is there any questions about last time? Please ask me now or later. So now is a good time.
What is that if necessary point in the 2B, like when it is not necessary?
So I'm saying that C transpose W is less than C. What we know is C transpose W is not equal to 0. So that means moving in the direction W. So C is this vector, W. So let me draw it with a pen. So C is this vector, and W is this vector, suppose. Okay. So if you take the dot product of C and W, it is positive. The angle is acute. Okay. But I want C transpose W to be less than 0. So what I will do is, if this was the case, that is the W that I was handed in step 2 here. If this W was aligned in the positive direction of C, then I replace W by minus W and then continue the argument. That was what if necessary meant. So if W had a positive dot product with C, then replace W by minus W. Okay, now we can assume that W has a negative dot product with C. That means moving in this direction would cause the objective function to reduce, which means moving in this direction would cause the objective function to increase, but we know that it cannot increase indefinitely. There must come a point at which you are about to step out of the feasible region. Stop at that point. What must have happened? One more coordinate must have become 0. Is that okay now?
Yeah, thank you.
The if necessary was just to ensure this. Any other questions? Okay. So, yeah, the plan today is to talk about the simplex method. And the simplex method is a method for solving LPs. And the way we are presenting the simplex method, as it is in the book, is for LPs in equational form. Okay.
I had a question. Can you please scroll up?
Sorry.
I had a question about the basic feasible solution proof that you just
Theorem.
mentioned.
Yeah.
The thing is, when we reach an x1 in case 2a,
Yes.
why are there going to be more zeros? Can you repeat?
Why are there going to be more zeros? So let us see. So maybe I will write here. So let us see. Let me just draw. This was your x naught. Okay.
Right.
Then, yeah. So this x naught had, let's say, it was feasible. So it had positive coordinates somewhere, and these were the coordinates which were k, and the remaining were 0. Okay. And now we are going to add some p times w.
Right.
Okay. And w has non-zero coordinates only in the same places where it has positive coordinates and it has zeros here. Okay. And it has non-zero coordinates here. But we don't know if they are positive coordinates or negative coordinates,
Right.
positive values or negative values.
Right.
But in 2a, w and minus w have the same status because both of them are orthogonal to C. Okay. So we will adjust
Right.
w so that these numbers become negative. Yeah, just I'm sure others also probably. Yeah. So some of them might have become, yes. Let us say we just ensure that at least one coordinate is negative. Now, as we move in that direction, moving in that direction means increasing the value of t. Yeah. So we move in that direction, and what will happen? This negative and this positive will collide. And at some point, one of these positives will threaten to become negative. At that point, that positive has become 0. Yeah. And we have got a solution where those that were 0 continue to be 0. And one more of these coordinates has also become 0. The remaining coordinates are non-negative. It continues to be a feasible solution. And since we moved in the direction W, where the objective function was not changing, the new objective function continues to be the same as the objective function value at x.
Right. Thank you.
Yeah. Okay. Good. Thank you. Yeah. Yeah. So just think about these. There are two cases. One is a very happy case, and the other splits into two cases, which again become happy. So, all right. So what we will do is see, I mean, the simplex method can be stated abstractly for general systems of, several linear equations and several variables, etc. But I think heart of the problem, heart of simplex is a very simple principle. And the book takes the viewpoint that initially it will just do examples. And after doing the examples, one realizes that how it should be stated in the abstract. Okay. So my plan today is just do the examples. Okay. And I think you have done enough to be able to write those examples using general variables which stand for matrices. Okay. So let us start. So suppose you have an LP. Yeah. So right here we have an LP in equational form. Why is it in equational form? These constraints are all equalities, and the only inequalities appear in the non-negativity constraint. Yeah. And so in general, we would call this part AX and this part B. Okay, good. And we are trying to maximize some objective function. Yeah. Now, it looks like this LP probably came from some other LP where there were inequalities, and we artificially added slack variables so that everything became equality. That is the case, but that's not important to us right now. Okay. So we have this situation where there seems to be a little, so if you look at the matrix corresponding to this equation, this set of equations here, it looks like this. But there is a little identity matrix sitting here, which came from the slack variables. Okay. So what we can do is, in this case, we are also in a happy situation where our right-hand side are all non-negative. So we just go ahead and happily find one basic feasible solution. How do we find one basic feasible solution? This variable, which is x3, we assign it the value 1. Yeah. x4, we assign 0. And x5. So yeah. So we take the right-hand side of our equation and just assign them to the slack variables. This is a basic feasible solution. Okay. Then, so we had these equalities, right? So we rearrange the equalities so that these variables, they are on one side and the other variables go to the other side. So the general principle is that the variables which are in the current basis, so over time, the basis will change. In the simplex method, the basis stays implicit. We don't keep, going back to the matrix and looking into it and seeing which are the basic basis will keep happening itself. But the point is that there will be some variables which appear on the right-hand side. I would like you to think of them as independent variables. That is, we can assign them values. And the moment we assign them values, these are dependent variables. They take up values so that the equations are all satisfied. Because all we have done is rearranged each of these equations. So we are free to choose the values of x1 and x2. And once we choose the value of x1 and x2, we are forced to assign x3, x4, x5 in this fashion. And now I'll let you imagine that whenever you have a basis, and that means you can assign the remaining variables whatever values you want, take them to the other side. And since these are, the basis is an invertible matrix, invertible square matrix, you can take its inverse and find values for the variables corresponding to the basis. So you can always write the variables corresponding to the basis as dependent variables, which depend on the freedom that you exercise in choosing the other values. So the other values you choose, and then you get these dependent values. But we must ensure that the values we choose, for us to be feasible, everything should come out to be positive. But right now we are in that happy situation because we are in a situation where all the dependent variables all the independent variables have been set to 0. Yeah, the only variables that have been set to non-zero perhaps are these 3 variables. It so turns out that in this case, x4 also has been set to 0, but that's just a coincidence. Okay, so we are in the current situation where all variables on the right-hand side have been set to 0, and these variables have been adjusted using this basis, but that will just stay abstract for us. Explicitly by these equalities, these variables have been adjusted so that all the equations are satisfied. Okay, now, so these variables can be expressed in terms of the other variables. And since we can do that, let us go and look at the objective function. And whenever a dependent variable appears in the objective function, we replace it by the right-hand side corresponding to that objective function. So in this case, because the objective function did not have any of these slack variables involved, yeah, it just stays as it is. So this is called for us the simplex tableau. Okay, so simplex tableau consists of the variables corresponding to the current basis on the left, and the equations have been rearranged so that these variables appear on the left with equality signs here, and the first equation tells you the value of this variable, the second equation tells you the value of this variable, the third equation tells you the value of this variable based on the independent variables. And the only things that appear in the objective function here are the independent variables. Okay, so is that clear? So this is how we are going to start.
X4 is minus x1, right? There is no 3 there, is there?
Oops,
Yeah,
oops.
it's
Yeah, so
fine.
there was a mistake. Yeah, there was a mistake. I don't know what I did. I don't know why. I seem to have also solved it using a 3. So maybe my original equations were written wrongly. That couldn't be, right? Okay. So what should I do? How did I get that? So
Change the original equation.
no, so yeah, so I could either doctor the original LP. Let me just put a 0 and see what happens. Yeah. Okay. So x4, x4 was minus x1. Okay. So let us stay with this. Let us see what happens. I have a suspicion because I solved it with this as 3, but maybe it didn't come into play at all. Okay. So now, good. So we have this situation. Yeah. So I might stumble a little later, but right now, let us just, yeah. So this is our tableau. Okay. So I seem to have made, let us see if there is a problem here. But yeah. So according to what I have written here, I should have written 0 here. Yeah. This 0 is this 0. Good. So now, look at the objective function. And it says that, yeah, so I made a mistake, obviously. Let me just look up the book for the example and then see whether what went wrong. Yeah. Okay, so I do see a 3 there. So what was, yeah, okay. Thank you. Yeah, so I made a mistake. I don't know why I wrote a 0 there. So this was meant to be a 3. Thank you. Yeah, and so I said something about coincidence, but there was no coincidence. This was 3. And this is a 3. Okay, now it's all right. Okay, yeah, good. So now, at this point, you see, so let me just go through the motions, then we will see what the principle is. But right now I see that I have the current solution that I'm sitting at is this. X3 has been assigned some value, X4 has been assigned some value, X5 has been assigned some value, and X1 and X2 have been assigned the value 0. And that is where I'm sitting, but I have carefully written the objective function in terms of the independent variables. Okay. And this seems to say that if you are trying to maximize, it will benefit you if you increase either X1 or X2. Okay. So we should be able to get a better value than what the current solution offers us by increasing the value X1. Okay. So let us attempt to increase the value X1. So as we increase the value X1, because so it's an independent variable, we increase it. As we increase it, these dependent values change. For example, if I set X1 to 1, X3 will become 2, and X4 will become 3 minus 1. Sorry, what did I say? Also 2. Okay, yeah, it also becomes 2. Yeah, that's a coincidence. Okay, yeah. And then as I increase X1 more and more and more, at some point, this equation is going to start complaining. Why? Because X4 will have been assigned a negative value. So what we do when we go down this route is we increase the value of X1 just to the brink where X4 becomes 0. That is, we set X1 to 3 and rearrange this equation so that X1 becomes an independent variable, dependent variable, and X4 moves to that side. So that is what has happened in the middle equation. I'm now thinking of X4 has become 0. So X4 has become 0. So it can be made a dependent variable and independent variable, and all independent variables we are supposed to keep at 0. So since X1 has now become 3, we move it to the left and rearrange this equation so that X1 is on the left and X4 is on the right. Okay. Good. But dependent variables should not appear on the right-hand side at all. So this x1 also needs to be replaced by 3 minus x4. So if I substitute for this x1, 3 minus x4, I get 4, and that minus x4 shows up here. In other words, I use these two equations to somehow eliminate. That is, you probably added this equation to this equation and moved x4 to the right. So if you add this equation with this equation, or rather this equation to this equation, this x1 will cancel. Yeah, so I have eliminated x1, and now I leave x3 on this side, and the x4 that showed up here, I move to the right. So whether you are substituting or whether you are adding a multiple of one equation to the other, they are the same thing. Yeah, this we know from high school. Yeah, there are two ways in which we are taught how to solve system of linear equation. Either you substitute values from one equation into the other, or you do some elimination by cleverly multiplying one equation and adding it to the other. They are the same thing. So that is what we did here. And luckily, x5 did not involve x1 anyway. Yeah, so there was no x1 sitting on the right, which needed to be cleared and replaced by x4 or some combination. So we are okay with that. So this equation stays as it is. And now in the objective function also, yeah, we again eliminate this x1 and replace it by 3 minus x4, and we are in this situation. So is that clear? In each step, some variable enters the basis. Which variable has entered the basis here? X1. And which variable left the basis? X1 caused some variable to become 0. Okay. And in this case, X4 was that variable. So it left the basis. And nothing happens as far as the equations are concerned. We just write them in a different way, just rearrange them so that some variable appears on the left and some variable appears on the right. So unfortunately, I'm going to be telling you everything very mechanically. Okay, and it's important to understand the mechanics because later on deeper things come out of this mechanics. Okay, so this is one of those computer science exercises. So we will derive mathematical theorems later on by doing this mechanical process and proving properties of this mechanical process. So right now, let us try and understand this mechanical process and trust it. Yeah. Okay. So we have come to this situation where we have a new set of independent variables, and these have become the dependent variables. And it turns out that the column 1, 3, and 5, if you look in your matrix A, they will now have become the basis. Okay, so they will be independent. Why that is the case is some linear algebra. Right now, don't worry about it. We have managed to write x1, x3, and x5 in terms of the other variables. That's all that is important. Okay, we don't need to keep looking at whether the set of columns is linearly independent or not. It will be. Okay, good. Okay. Now, we again see some prospect of improving our objective function. That is, x2 can be increased, and then the objective function will increase in value, because right now x2 and x4 have been set to 0. Every variable that appears on the right has been set to 0, and this is our current solution, 4, 3, 2, for x3, x1, and x5. So as we increase x2, the same principle applies. This equation says that you may increase x2 up till 4. At 4, something will start going wrong. Yeah, but this equation says, I have no complaints. You are free to increase x2 as much as you want. Nothing goes wrong with x1. But x5 is even more picky than x3. It doesn't allow you to let x2 go more than 2. So we do what we can. We push x2 to 2. That means we just exchange x2 and x5 in this equation. So you get this. Yeah. And wherever x2 appeared on the right, we have to now replace it by 2 minus x5. So wherever x2 appeared, we have to replace it by 2 minus x5. So if you replace this by 2 minus x5, did I make a mistake?
It should be 2 plus x5 minus x4. Right?
Sorry, x2 is 2 minus x5, right?
So 2 plus x5 minus x4.
So this should have been a plus, right?
Yes.
Is that what you're saying? Yeah, you're right.
Yes.
Yeah, thank you. Yeah. Okay. Yeah. So very bad at this. So anyway, so this should have been 2 plus x5. Yeah. So I have substituted for x2 the value 2 minus x5. So this became, yeah. Or I could say that I have subtracted the last equation. I've subtracted the last equation from this equation. As a result, this x2 goes away. This 4 becomes 2. I get a minus x5 on the left, which I move to the right, and it becomes x. And this I had rearranged. Yeah, this was the genesis of everything. And the second equation was unconcerned. Yeah. And then in the objective function, I replace it by 2 minus x5, and we are in this situation. Good. So now it turns out that we have these independent variables, x4 and x5. x1 and x2 and x3 have become dependent variables. But if you increase x4 or x5 from its 0 value, the objective function is only going to reduce. So we don't have a way of improving the solution locally using the simplex step. This step is called the pivoting step. Yeah, it is very similar to pivot in Gaussian elimination, especially if you think of substitution as subtracting certain or adding certain multiples of one equation to the other. Then it is the same as Gaussian elimination. Actually, what we are doing is a little Gaussian elimination step. But while doing the little Gaussian elimination step, we are looking over our shoulder and checking whether some variable is going to turn negative because of that, with our convention that dependent variables have to be set to 0. Yeah. So with that additional care, it is like Gaussian elimination. Okay. But we have come to this situation where the coefficients of the variables which appear in the objective function below this horizontal line, they are both negative. The claim is that we have reached the optimum of the linear program. Okay. Why? Because these equations are the same as previous equations. So if I set x3, x1, x2, I will get 2, 3, and 5. And under that setting, because I have only been substituting throughout, the objective function value will be x5 because x4 and x5 have to be set. So certainly this solution achieves the objective value of 5. And it cannot achieve anything better than 5 because any substitution that you do for the variables has to satisfy these equations. But in particular, it has to satisfy the non-negativity.
So the termination step happens when in the objective function every coefficient is negative.
Every coefficient here. So yes, there are many termination steps, but one of them, at least the optimality is achieved when everything other than this constant term, yeah, every variable, as you said, has negative coefficient, yeah, or 0, yeah. Okay. So why? And I'm just trying to give you, so not only, I mean, it's not optimal because I say so. You see from this that yeah, so let me just say it again. At any step, you can declare this to be your objective function and these to be the set of equations and the non-negativity constraint stay as it is. The same original LP, and you can turn this into an LP by saying I want to maximize x1 and x2 subject x1 plus x2 subject to these constraints and these variables being positive. The original LP and this LP are the same because all that you have done is you have taken some equalities and substituted their values here and there. Okay. So yes, so whatever we have got here, you can go back from this to the original one. So this LP and the original LP, this is not written in the LP form, but I could have said maximize this subject to this. Okay. That LP and the original LP are the same LP. because all you have done is substitution for variables. That substitution had a certain method for doing substitution, that is the simplex method. Okay, but all that you have done is substitution. You could have also done other wild substitutions and your LP would have stayed the same. Yeah. So what we know now is that the final LP we have got, its objective function value is the same as the objective function value of the original LP. And we know by inspection itself that this LP cannot take the value better than 5, because there is non-negativity constraint on x4 and x5, and the best you will be able to substitute is 0 and 0 for them. And when you substitute 0 and 0, we get values for the other variables which turn out to be non-negative and so are feasible, and they achieve the objective. Okay. And not said it very well, but is it clear that once you get here, you can, I mean, you have to stop because you don't know what to do, but that's not the only reason. You can even convince someone that what you have at present is the best solution, because no matter what anybody does, they will have to set x4 and x5 non-negative, and they will not be able to get a value better than 5. There was a question.
But setting x4 and x5 to 0 would not necessarily mean that x1, x2, x3 are greater than equal to 0, right?
In this case, they are, right?
In this case, yeah, but I mean in general, when
no. So that is why we start from feasibility, and whenever we are at any tableau, every tableau will maintain, we will maintain the invariant that if you set the independent variables to 0, the dependent variables will acquire non-negative values. This will be an invariant we will maintain throughout the process. Okay, so we started, but at least you agree that if it was true at one step, the pivot step that we do it carefully enough so that it continues to be true. That you agree, right?
Yes. Yes.
Yeah. So if we had an initial basic feasible solution and we had rearranged the equations in this form, then onwards we are safe. Okay. And if we are lucky enough to reach this situation, then we can be sure that we have reached the optimum. That is all I wanted to say at this point. Okay. So there are many problems with, this was a very kind of a nice situation. It was easy to start because there were these slack variables and the right-hand side was non-negative. Yeah. So I could set the slack variables to the right-hand side value and then keep churning my LP. And it seems that when I needed to stop, I came to this situation where I could not make any more progress. But then when I can't make progress, there is no progress to be made. Yeah, nobody can make progress. And since I had that argument, I can claim that I have solved the LP. All right. Okay. Now, yeah, any questions? Yeah.
But okay, first you have to find the feasible solution itself.
How do you find the feasible solution? Whenever you have a situation like this, where the right-hand side is all positive and you have a slack variables, then the situation is easy. Otherwise, we need to find a feasible solution itself, and that's a problem we will address. Yeah.
Actually, finding a feasible solution itself is as difficult as solving a LP, right?
That's right. Finding
because you can do binary search on the objective function.
That's right. So yeah, so Srijato is right. So finding the optimum of an LP and finding a feasible solution of an LP, they look like different things, but actually they are the same. Binary search is one method, and maybe 2 classes from now we will see that there is another method, yeah, which will tell you that finding a feasible solution is the same as finding the optimum. So it looks like we are kind of painting a very rosy picture, but maybe even to start this process is going to be impossibly hard. So is there a catch in all this? So those are the things that I want to address one by one now. Okay. Yeah. So okay. So if there are no questions, so there are 3 or 4 points which I would like to address. And once I do that, then my informal example-based description of simplex method would be complete. Okay, so I have not done that. Actually, not everything I'll be able to say. Yeah. So yeah. one of the points Srijato also already pointed out, but there is something else also I want to tell you before that, and then I'll come to Srijato's point. How do we even start? How do we get the starting position? Because nobody is going to necessarily embed an identity matrix and a non-negative right-hand side for me. Okay. Yeah.
So I have one question.
Yes.
So are we basically trying to find a basis where setting the basis to 0 will give you a...
No, it's setting everything other than the basis.
Sorry.
We are trying. Yeah, good point. So I should have said that. So you have this matrix A. We will set everything outside the basis to 0. So now we are left with a square matrix. Some variables correspond to the square matrix and a right-hand side. And this square matrix happens to be non-singular. So we can solve them by inverting the matrix or doing Gaussian elimination. Okay. So a basic feasible solution is indeed such an object. And we are trying to find a solution, a matrix, that square matrix, so that when you do this inversion, somehow by luck, all the answers that you get turn out to be non-negative. That's what we are trying to find. Okay. We start with one which satisfies that property, but is not necessarily optimal. And from here, we somehow slide into a situation where things are optimal. All right. Any other questions? Now, see, sometimes what can happen, for example, here is an example, and let me just show one step. So rewriting this, again, we were in this happy situation where there was a little identity matrix embedded here. So I can declare x3 and x4 to my dependent variables or the basic variables. Yeah. And I have written the basic variables in terms of the rest. That means if I set them to 0, I get solution 1, 2, which is non-negative. Okay. And my objective function anyway did not...
Screen is not visible. Is it just me, or
it's not visible at all, or
I mean, only your camera is visible, not the screen? Is it just me, or
can people see my sheet of paper?
Yeah, we can see. I think it is for you only.
Okay, now it's visible. Okay, sorry. It was mine. So.
No. Yeah. No, thanks for checking. Yeah. Yeah. So yeah, please stop me if yeah. So let's say that this was your LP. So when I write a Tableau from now on, you should understand that what I write here is the objective function, and these are the equations somehow written in slightly perverse way. Some variables have been declared as dependent, some variables have been declared as independent, and there is always a non-negativity constraint floating around, which is never written. Okay. Yeah. So that is what the Tableau does for us. Now we are in this situation, and we notice that if we increase x1, the objective function will increase, and this puts a constraint. That is, once we increase x1 to something like 1, then x1 can no longer be called an independent variable because it has acquired a positive value. So x1 better move to the left, and then x3 moves here. And wherever x1 appears, we have to eliminate it. So if we added these two equations, somehow x1 and x2 both seem to cancel, and this x3 moves to the right here, and we get this. Okay. And similarly, for this x1, we are supposed to substitute 1 plus x2 minus x3. Okay. So you understand we are in this situation, and it looks like, okay, we can make further progress by increasing x2. This is the same LP as the previous LP, just written in terms of different variables. Yeah. So we have substituted for some variables, so that because we had equalities, we could substitute for some variables, and we have written everything in terms of the independent variables now. And now this x2 can be increased, and the objective function can be increased. Yeah. But how much? At some point, we should get stuck. So we examine this equation, and we ask, as we increase x2, what effect does it have on x1? Well, as we increase x2, x1 becomes 1 plus x2. So it looks like x1 is never going to complain. x1 is going to stay non-negative. And what about x4? x4 says that you may change x2 as much as you want. I don't change at all because my value only depends on x3. So it looks like I can increase x2 indefinitely. And since this was the same LP as the original LP also, I can get arbitrarily large solutions. Okay. In fact, so whenever this happens, yeah. So last time someone asked, when do we terminate? When all the coefficients become negative. Here, coefficient has not become negative. There is a positive coefficient. Yeah, strictly positive coefficient, +1. But we are unable to perform the pivot step, at least what we have been told to perform as a pivot step. Okay, wait for some equation to complain and then switch. Okay, there is no equation is complaining. Now it turns out that this is a sign of unboundedness. That is, the original LP itself was unbounded. And why is that the case? Well, if you look at, so I mean, one is by inspection itself, it is unbounded. But if you look at the solution, the current solution is 1, 3, sorry. The value for x1 is 1, the value for x4 is 3. Yeah. And x2 and x3 have been set to 0. Yeah. x2 and x3 have been set to 0. This value is 1 and the last value is 3. Okay. Yeah. But if I parameterize by x2, yeah, I can substitute any value for x2. Then I get a solution like this. x1's value is 1 plus x2. Let me set x3 to 0. Yeah, set x3 to 0. Or sorry, what did I do? There's a mistake here, I think. Okay. So set x3 to 0, and then we get a solution which is parameterized by x2. Yeah. So if you look at only this, it satisfies all these equations and it is parameterized by x2. And notice that no matter what value you put, what positive value you put for x2, this will continue to satisfy the equations and will continue to be a feasible solution because non-negativity constraints will be satisfied. But then what do we notice? That the objective function is going to shoot up based on x2. So what we have is that the original solution, yeah, so there is this original solution here, 1, 0, 0, 3, and there is this direction of movement. As x2 moves, we add 1 to the first coordinate and the second coordinate, and our objective function, yeah, if you take its dot product with this vector, yeah, this part, because of this coordinate, it is positive. That is, this movement in this direction and the current objective function, that is this part of it, they are aligned in the same direction. So moving along this ray indefinitely, yeah, is going to make your objective function arbitrarily large. So most probably the feasible region is perhaps something like this, which allows you to move in this direction arbitrarily. Okay. So again, it's sometimes hard to see the geometry and the mechanics at the same time. I think it is perfectly fine to think of this very mechanically, saying that we are in this situation and we are free to increase x2 to whatever we want, and so the LP must be unbounded, and we can just stop there. Yeah. So is this clear? Now it turns out that whenever the LP is unbounded, yeah, there is one small caveat, but you will come to a situation where this will happen. Okay. So when we prove the correctness, or when we state the correctness of the simplex method, we'll have to say that the simplex method will stop after a finite amount of time. And if the original LP is unbounded, then it will reach a situation like this, where there is a coefficient in the objective function which is positive, and its coefficients in all the equations above are non-negative. It is 0 sometimes, never has a negative coefficient in this part. If this variable, which has a positive coefficient here, never has a negative coefficient here, then that particular variable can be increased indefinitely, and this objective function can be boosted. So this is another way of termination when you have an unbounded LP. So you terminate if coefficients become negative, or you terminate if there is a positive coefficient which allows you to push the objective value indefinitely high. Yeah. Okay. Any questions? So this was the first statement I wanted to make about simplex getting stuck. Yeah. So this is not actually stuck. I mean, not just simplex. It is a sign. Whenever you get stuck in this situation, it's a sign that the LP is unbounded. Okay. Good. Now, the next thing I want to talk about is degeneracy, and I will not completely resolve this situation today. We'll need to talk about it next time a little bit. Okay, but let me just describe to you what degeneracy is. Okay, and so, sorry, are there any questions? Everybody is very quiet, and I don't know if it's too obvious or it's. Yes.
I have a question, but I'm not sure how to phrase it.
Yeah, please go ahead.
Yeah, so here we are fixing one of the independent variable and parameterizing with respect to the other, right? So is it to detect such a situation?
No, we are parameterizing with respect to. We are parameterizing with respect to this.
Yes, yes. So to detect such a situation, is it like should we just do it like parameterize with respect to each independent variable and then see if this coefficient vector is positive?
Yeah, the parameterization was just to show to you that there is a ray where along which the objective function increases indefinitely. But when you come to this situation, you look for a variable which has a positive coefficient, because that's what simplex method tells you. So you try to, and if it turns out that none of the equations puts a restriction on this variable, then you can stop and declare the LP to be unbounded.
Okay.
And why can you declare it to be unbounded? Either you can just say that this is the same LP as the previous one, so obviously it is unbounded, why are you arguing? Or if you want to think geometrically, you can say that this situation offers us a parameterized solution of this form, where there was the original solution, and this variable, as you increase it, it perturbs these variables based on the coefficient here, and that amounts to moving along this ray. And as you move along this ray, the objective function seems to have a positive coefficient, dot product with this ray, yeah, this part. And so the objective function will increase. But this is just to reinforce it for us. This already is a witness to the fact that the LP is unbounded. Was that the question? I don't know.
Yeah, I got it now. Yeah.
Okay. So now we have a situation here where when you set x1 and x2 to 0, x3 also has become 0. Yeah. So there was no, the constant term here was 0. And then x4 was 2 minus x1. And your objective function happened to be x2. So now, since x2 is an objective function, x2 has a positive coefficient here, we would like to improve the value of z by increasing x2. How much can we increase x2? x4 is oblivious. x3. The problem is x3 says, don't even touch x2. The moment you increase x2, I'm going to get into trouble, because x3 will start becoming negative as we hold x1 at 0. So what we do is we kind of go through the motions and we say, okay, we seem to have hit the wall right at the beginning itself, but all right, we will just exchange x3 and x2. So we put x2 on this side, x3 on this side, and adjust the objective function by substituting the value for x2 from here, and x2 got substituted by x1 minus x3. And now we again notice that x1 can help us improve the objective function. And if we do that, here x2 is not worried about x1 because x1 can go up and x2's value can only improve. But this equation starts imposing a constraint on the value of x1, which is 2. So we do a pivot with respect to this. This moves out of the basis. X1 moves into the basis. And I hope I've done it right. Yeah. So instead of x1, we write 2 minus x4. Yeah. And instead of this x1, we write 2 minus x4. And we are in the original situation where all the coefficients have become negative, and we can claim that the optimum value for this linear program was actually this quantity 2. Okay, and this is a witness to that fact. Yeah, nothing needs to be said. Now, so in this case, what happened? There was a move here. We seem to have, simplex seems to have worked hard, rearranging a certain equation and substituting values for the objective function. But actually, if you look at the underlying solution, what was the solution here? x4 is 2, all other variables are 0, some because they are independent and are meant to be 0, and some because even though they were dependent, the value, the constant value here was 0. Okay, so some values were 0. x4 was the only value which was at 2. When we did one step of the simplex method and you asked, what is your current solution? Where are you sitting? You seem to be sitting at the same place. Yeah, it is just that you have now chosen a different basis with respect to which it is also a basic feasible solution. Earlier, it was a basic feasible solution with the basis as column 3 and column 4. Now it is a basic feasible solution with column 2 and column 4. Okay, and sorry, is that right? Yeah. Okay, and here x3, even though it is participating in the basis, when you inverted the matrix and tried to compute the value for x3, it turns out to be 0. Okay, and here, so it is a situation where x4 takes the value 2 and the remaining variables are 0. Now we are in a two-dimensional system because we have two equations. So this x4 can be combined either with x1 or with x2, and it will still has a right to be called a basic feasible solution. And we seem to have moved from one to the other. But once we moved here, something opened up and we were able to move further and get to the optimum situation.
So suppose you make a sequence of such pivot moves where the objective value does not change, then is it not possible to cycle back to a same basis you started before? Yeah.
So it is possible that, so here, that's what, so something new opened up. Are we guaranteed that something will open up? Or,
yes, exactly.
Yeah, or could it be that we will come to a situation where all coefficients, or at least one coefficient, becomes positive and we are able to declare the LP to be unbounded? Yeah, so one of the earlier stopping criteria, will it always be met? Okay, now if you just do these operations, yeah, stupidly, yeah, it is not going to happen. I mean, it is possible for us to cycle. Okay, cycling is possible. Okay. Yeah. Now, there is a certain discipline you can adopt when there are multiple choices for entering the basis and exiting the basis. Okay, and if you adopt, so there are examples where cycling can happen, where in each step you are doing a legitimate simplex operation. Okay, but there is a way of saying that look at the smallest variable among those that can enter the basis and move that in. Then one can prove that after finite number of steps, either you will meet one of the two termination conditions, or you will have moved out of this cycle, this potential cycle, into another place. So eventually you will terminate. So what I'm saying is that by adopting a certain strategy for which variable should enter when there are multiple choices and which variable should leave, it is possible to prove that simplex method will terminate. Okay, and this is not something that I'm going to discuss today. This we will do next time. Okay, so one of the rules for the choice of these variables is called Bland's rule, and we will discuss that next time. Okay, so today I just want to so I just want to do the other things, and next time we will discuss Bland's rule. Yeah, but your question is valid. It is possible in general for things to cycle. Yeah.
So Jaykumar, in a non-degenerate case, we're always improving the objective.
In non-degenerate case, we are improving the objective. Thank you. So as long as some variable, if you are able to change the value of the variable so you are trying to make an independent random, I don't know why I always say random with independent variable, you are trying to increase its value. And whenever you increase the independent variable's value, the objective function increases. Okay, so when you cycle, that means at every step, you were just sort of imagining in your head that you are making progress as far as simplex is concerned, but you are stuck at the same solution. Okay, so if you are able to increase the value of an independent variable, your objective function has changed, so you could not have been the same basis. Yeah, so when you are in a tableau, the value that appears here as the constant term is the current objective function value. Yeah, so in this also it is 0, in this also it is 0, stands to reason because the two solutions are in fact the same. Here the objective function value is 2. Okay, and the moment you perturb x1, this will increase from 0 to something, and then onwards it's not going to reduce. Yeah, so we are going to climb, and we just need to guard against cycling. Okay, so now I finally come to Srijato's question. So where to start? Yeah, how do we? Yeah, so how do we even start? You may not always have. So once again, if your LP in equational form arose out of an LP where you had inequalities and you introduced slack variables, and it so turned out that the original LP, like problems like vertex cover or things that might have come out of covering problems, there you want something to be greater than or equal to some value, 1 or 5 or 7. Okay, so if the right hand side turned out to be non-negative and you had the luxury of these slack variables, you have a legitimate way of starting. But LP is an LP. Okay, so we could have a situation like this. Okay, and it is not clear, or how do we even say, how do we assign values to these variables so that we can start? So here is a trick, and so Srijato pointed out that finding a feasible solution is as hard as solving the LP. We are going to turn it around and say that finding a feasible solution is as easy as solving an LP, but solving an LP which has a natural feasible solution. Otherwise, we are just going in circles. Okay, so we are given some LP. We will design an auxiliary LP. Okay, that auxiliary LP will have a natural feasible solution to start with, basic feasible solution to start with. Okay, and the result of that auxiliary LP will provide us a basic feasible solution for the original LP, and from there we will continue the simplex and use Bland's rule to finally terminate. Is that clear? So Now,
Sorry, Jaykumar. We can always assume feasibility, can't we?
we assume that we can assume that the LP is feasible, but we need to start with a feasible solution. How do we know?
Sure. But feasibility we're taking for granted.
So that will come out of this
starting point, right, for simplex to begin.
No, so that's right. But she's Kavita's point was: are we assuming feasibility? So what this step, this auxiliary LP will tell you is if. So when this auxiliary LP first of all has a natural. So let me just praise this auxiliary LP. This auxiliary LP will have a natural starting basic solution. Point number one, and it will terminate because we know that all LPs once started will terminate. Okay. When it terminates, either it will give us a basic feasible solution to the original LP, or by examining what it terminated with, we will be able to declare that the original LP was infeasible. Okay. So I did not say it completely,
Sure,
and
thanks.
that's what was the cost. Yeah. So this auxiliary LP will allow us to do both. It will either tell us, here is your basic feasible solution, please go ahead and solve your original LP starting with this, or it is going to say, sorry, there is no feasible solution to your original LP. That is what this auxiliary LP will do for us. Okay, so let me just quickly tell you what the auxiliary LP is. So what we do is we have this, in this case, so let me just do it with an example. Yeah, so we have these this LP here, and let us pretend that we don't know how to find a basic feasible solution for this right now. So what we do is, to the first equation and the two equations, we add a new variable. So to this equation, we say plus y1, and to this we say plus y2. Okay, I hope, did I do that? So, sorry, yeah. Okay, so let me just say what we are going to do, and then I will do the example. So to each of these equations, I will add sort of a fake slack variable, y1 and y2, and we will set those values to the right-hand side. Okay, and we can assume that the right-hand side is greater than 0. Otherwise, these are all equalities. We will just multiply them with -1 so that the right-hand side is always non-negative. Okay, so we can always assume this. And then we do this slack, we create a fake slack variable, yeah, and we set them up. And then we ask the LP to get us an objective function 0. That is from here, yeah. So we want summation yi to be as small as possible. And since we are talking about maximization LP, that's why there are these ugly negative signs. I'm sorry if this is confusing. Try to find, so now we have got a basic feasible solution to this auxiliary LP. We don't work with this objective function. Our new objective function is this. Okay, or you can think of it as minimizing summation yi. Minimize summation yi subject to this. And now we have a starting basic solution with yi set to bi. Is this clear?
Yes.
Maybe. So let us do this example. So here it's the same example. I just copied it. Yeah, I hope. So now I set for each of them a new slack variable. And I maximize this. You should read it as minimize the summation yi. Okay. And I start with these set to 4 and 2. And where did this 4 and 2 come with? From here. And they are all, now these are our variables. There are 2 additional variables. And they're all non-negative. Yeah. Okay. And why are they non-negative? Yeah. Question.
Yeah, so the objective function over here need not have any relation to the objective function there, right? I mean,
yeah. So this is an auxiliary LP, whose objective is to find a feasible solution for the original LP. That means a feasible solution for this LP, for this LP, sorry, for this set of equations, a feasible solution where the yi's are all set to 0. A feasible solution here, where the yi's are all set to 0, is a feasible solution for the original LP.
yeah, right.
Yeah, and we have not increased the dimension here. That is the matrix. Yeah. So if in the end we find a feasible solution here, it will correspond to some basis here. That is, it will not involve hopefully any columns which we added now. Yeah. So we can then drop these y1, y2, pretend that they didn't exist, and continue the simplex method from there after having reintroduced the original objective function. Okay. So temporarily, we move to a different objective function, run the LP, and once we have found the solution, we move to the old objective function and continue from there. Always doing simplex steps. Okay. So let us do that. So what did I do? I copied something wrong, obviously, because the book doesn't. Okay, so so this x4 is supposed to be y1. Does anybody remember what I had? So instead of x4, I should have written minus y1, and for x5, I should have written, so let me not mess this up. Yeah, so you should think of this as minus y1 and plus y2. The book just wants to keep variables x all the time, and that's why. Yeah, I will correct it when I put the notes up.
There will be a minus y2 in the x3.
Sorry, there should have been a minus.
X3 is equals to 2 minus 2x2 minus y2.
That is right. Yeah. Okay, so yeah, so getting a little confused. What did I actually do? So one second, I somehow seem to have messed up rather badly. Anyway, I mean, the point is that in the first tableau that you get, y1 and y2 should have been the dependent variables, and the others should have been independent variables. So I seem to have missed one tableau completely. And okay, so my point was that if you did, so yeah, I was just being lazy. If you start with this and start with your original basic feasible solution, I have not shown all the steps. So these are many steps here, many steps. At the end, you will terminate here. Okay, and you are in a maximizing problem. So this should have been a minus. Yeah. So you know that you have reached the optimum, and the optimum value now is 0. Yeah, the optimum of this LP has become 0. So that means these yi's have been set to 0, and you recover the value x1 and x3 from here, which is 2, and x2 is 0. So you start with that basic feasible basic solution. X1 equals 2, x2 equals 2, and yeah, and you continue. I don't know what I'm doing. So, but it seems to me I'm saying that x1 is 1. Oh, sorry. Yeah. Okay. So, yeah, so once you do the auxiliary linear program, you come to this situation. Okay, you come to this situation. From this, you conclude that you have a basic feasible solution, x1, 2, x3, 2, x2, and x3 is, sorry, x2 has been set to 0. Okay, so now you forget the y's and replace this objective function by the original objective function. The original objective function was x1 plus 2x2. I'm sorry, I forgot about it. x1 plus 2x2, but x1 is 2 minus x2. Remember? this was x1 plus 2x2, but x1 itself is 2 minus x2. So if you substitute 2 minus x2 here, you get x2 plus x2. Okay. So once again, this was the entire run of the auxiliary program, which I did not do in detail, but it stops at this. Yeah, trust me. When it stops at this, these auxiliary random fake slack variables have already become 0. Yeah. So we are in a happy situation and we can continue from here. We discard this objective function, put back the original objective function, but in terms of the independent variables, and continue. Now, in this case, what I'm showing next is one step of the simplex method for this tableau. And in this, you can increase x2. How much can you increase x2? Well, you can increase x2 to at most 1. Yeah. So you increase x2, and I think if you try to solve, is this what happens? Yeah. So anyway, one step of the simplex method from here leads you to this. And at this point, what you realize is that all coefficients that appear in the objective function are, yeah, none of them is positive, they're negative. Yeah. So you have reached the optimum. Okay, please ask. This part was not very clearly done. I should have done this in greater detail. Yeah. But this principle is this. You set up this auxiliary LP, yeah, solve it, find a feasible solution. But what happens if this LP stops, yeah, and gives you an objective value which is negative? You're trying to maximize it, and it came out to be negative. We want it to be 0. Yeah.
How can the objective value, I mean, summation y is always greater than equal to 0, right?
Yeah, but there is negative signs here. Sorry. Yeah. So the objective function value for us is maximize this. So initial, when you put the initial solution was y1 is 4 and y2 is 2. What is the objective value? Minus 6. Yeah. So when you wrote the initial tableau, you would have actually seen a -6 here. And some coefficients. One of them probably was positive. So you increase that, and the y1 or y2 moved to the right. My claim is that after you did this step many times, you would have come to this situation. Okay. But who says that you'll come to this situation where you would get a 0 here? Maybe this came out to be -4. Yeah, you will never get more than 0. Yeah, because you're trying to maximize and you want to hit 0. Yeah. So if you are stuck with a negative value, this simplex stop, the auxiliary simplex stops with a negative value, then you can claim that the original LP was infeasible. Okay, so let me see. This auxiliary LP has at least one advantage, that we always have a starting basic feasible solution for it. Okay, so now when we run simplex with Bland's rule, it is going to terminate. It can terminate. Yeah, it can. If it terminates with with a 0 as its value. Yeah. So it is always bounded. This LP is bounded because I mean y1, y2, it cannot go above 0. Yeah, y1, y2 are non-negative values, so it can never go above 0. So, but if it hits 0, you have found your basic feasible solution for the original LP. If it stays negative, yeah, that means there is always some need for this slack here. Yeah. which means that the original LP did not have a feasible solution. Okay. So this is all I want to say for today. Yeah. Now, this looks like a mechanical procedure. Once we prove Bland's rule, then we have sort of in our pocket a statement of the following kind. That is, any LP at the end of the simplex is either going to tell us that the things are unbounded, and the proof or the witness to unboundedness will be that there will be a variable here, yeah, which has a non-negative coefficient, and we are at liberty to increase it indefinitely. Okay, either we'll be there or we will be left with a proof of optimality of the current solution. Now, once you have this with you, because of the correctness of the simplex method, it is possible to turn this into the famous LP duality theorem. Okay, so next time I will talk a little bit more about simplex, and I will state the duality theorem. So we will present several proofs of the duality theorem. One of the proofs we can say comes from simplex method. This is very similar to, say, when you do linear algebra. Some statements you can say, oh, you start with this matrix and I will do Gaussian elimination, and when Gaussian elimination terminates, either I get a 0 row or I get something, and from that I conclude some fact. Or some people can just sit back and think about vector spaces and say that, oh yeah, in a vector space with in RD, a subspace of RD cannot have dimension more than D, and hence something is true. So there is this algorithmic way of proving the same thing, but because you know that Gaussian elimination terminates and results in a matrix which is in row echelon form, and from the structural properties of that row echelon form, you conclude something. Or you do linear algebra in this abstract way in terms of vector spaces, bases, and linear independence, and prove the same thing. So I will next time try to make as much connection between Gaussian elimination and simplex method as I can. Some of which you already saw when you were trying to eliminate variables. And so the same theorem, the duality theorem, can be derived out of simplex method, just as many theorems in linear algebra can be derived out of Gaussian elimination. Or you can talk about convex objects in general, in particular convex cones, yeah, separating hyperplanes, and there will be theorems. There will be ways of proving the duality theorem using that sort of approach. Okay, both of them have value, and let us see, yeah, next time. So if there are any questions on what we did today, yes, simplex method, we said that we could terminate in two ways. Yeah, either finding an optimal solution with a witness of optimality, or in an unbounded situation with a witness of unboundedness. We were worried that we may never stop because we can cycle, and that worry exists. Yeah, and it arises out of degeneracy. Then we were worried
so
that we may not even
we need to show that that eventually we find such a certificate of either optimality or unboundedness. Is that
yes,
there are no cycles, right?
That's right. The only thing we have left to do is dealing with cycling. Yeah.
So
once we have
going back to Srijata's doubt or his remark earlier that finding a feasible solution and solving for optimality are equivalent via binary search. So couldn't we actually reintroduce the objective function as one of the constraints and do binary search and use your way to start method to actually solve the LP?
Sorry, say that again. So the
finding
objective
a feasible
function
solution.
Yeah.
So by discarding the objective function.
Right now we are discarding the objective function temporarily. Yes.
Exactly. So why don't we actually use it as one of the constraints is equal to some tentative value? And,
okay.
But by binary search, you have to do log n many LPs, and here you have to just do 2 LPs. So
Exactly.
Yeah.
So
2 is better than log n.
No, so yeah, no, so your no, but let me just try to understand Kavita's idea. So you introduce, you set some, so whatever we were doing for binary search, you're saying, can we combine the two steps?
exactly.
Yeah. So I think that you can do. So you start, you say, set the objective function to be the value, say, like if you had an upper bound of 1000, you set the objective value to 1000 and see whether this particular LP is feasible or not. And you find out that it is infeasible. Okay. That means you cannot achieve a maximum of 1000. You try 500 and again find feasibility using the same method.
Exactly.
Yeah. And this way you can solve. The other possibility is we first find a feasible solution and from there just run the LP towards optimality. So that would require just 2 runs, whereas this binary search method would require multiple runs. Yeah, that's both are fine. Yeah. Yeah, but we have once we have Bland's rule set up, we have a foolproof method of checking feasibility. Yeah. Because by introducing this auxiliary LP. Any other questions? I will try to write the last part correctly and then post it on Piazza. So yeah, so if there are no more questions, we can meet on Tuesday. And if you have any questions in the meanwhile, please feel free to send over email or post it on Piazza. I think so. We'll post the homework in a couple of hours. Yeah, maybe by this afternoon you will have the homework on Piazza. Okay. So once people leave, I will.
Yeah. Thank you, sir. Bye.
Yeah. Kavita.
So can we use this Zoom link or is there another lecture?
Should I send you? There will be a Ramprasad's lecture at 11:30. So.
Okay, so we have time till then.
Or should I send you another one? I mean, how long? Yeah, might as well, right? Or what do you want to do? Maybe we, but 10 minutes. Yeah. Let us just, let me send you another one. I think, yeah, because might want to log in early and then it will be a mess.
Sure.
Okay, so I'm ending this. Yeah, and then I will send you within